In this tutorial, we'll see how to use Digitalis to run structural optimizations of the lattice structures. In the last tutorial, we built finite element models of our lattice designs and exported them to either Caramba or Abaqus. Here on the right is an example of a lattice structure turned into a Caramba model. It is a cantilever type model with a lattice structure fixed to the left and submitted to a vertical load downwards on the right. It is also contained within two plates at the top and at the bottom here. The lattice elements are made of beam elements and the top and bottom surfaces of shell elements. With Caramba, it's possible to view the cross-section of the beams as they are at the moment. And this is the structure we have at the moment before optimization. So it is a homogeneous structure with all the elements having a 0.1 mm radius. Now let's move to the optimization components. So, the optimization components are stored within the strut optimization panel. There are 4 components, 2 with Caramba, 2 with Abaqus, which run very similar optimization algorithms. In this tutorial, we'll demonstrate using the Caramba-based components, but it's possible to run the same optimization using the Abaqus-based optimization components. So as you've seen, there are 2 possible section optimization components, number 1 and 2, which differ by the number of parameters they require from the user. So section optimization 2 requires a higher number of parameters, which also makes it a bit more flexible. Here we'll use the simplest one, which is the section optimization 1. So the section optimization algorithms are based on the concept that the cross-section of each individual element is updated until all of them reach a target strain, which is one of the main inputs from the user. Other inputs include the minimum and maximum diameters possible for the strut elements, and another important parameter is the iterations parameter, and that's the number of iterations the algorithm is allowed to go through. So if we start in our scenario with a target strain of 5 millistrain, we can also start with a fairly small number of iterations just to have a look at how it would work. So we will trigger the optimization by turning this run boolean to true. And we'll start seeing some information from this component in the Rhino window. At the end of the optimization process, the time it took to run the optimization is displayed in the Rhino window. So this optimization took 20 seconds. Obviously, it was with a very small number of iterations. Using more iteration would increase the time it takes, and larger models would also take longer to run. So here, 10 iterations were already enough to see a very clear trend in the optimization. It's no longer a homogeneous structure. We can see that clear paths of load distribution have appeared. The section optimization component outputs the updated diameters, so the result of this optimization. It also outputs the strains or the deformations within all the components of the lattice. And it also gives information on the convergence of the structural adaptation. And so if we have a look here, it seems that with 10 iterations, we haven't reached convergence of the structure. So we can rerun this optimization with a higher number of iterations. To do this, we'll disable the optimization process here on the Boolean toggle before making the changes and try with, for example, 25 iterations. So we'll start the optimization process again. And this time, with 25 iterations, the optimization took 28 seconds. Now if we check the convergence curve, we can see that we've reached stability in the structural adaptation. And if we look at the 3D design we now obtain, it is very similar to the design we had for 10 iterations. So this type of optimization is possible for a high number of different loading cases, arbitrary loading scenario, boundary conditions. It's possible for different size of model, different cell types. And it's also possible to use the section optimization components to optimize the lattice designs to a combination of load cases, and this way find the best trade-off for structures that might be submitted to different load cases at different time points, for example. The grasshopper template for this simple optimization scenario, for using Caramba models or Abacus models, is available to download on the website.